Hello everyone. This is the video lecture of section 8.6 part 2 of calculus 2 math 2520. So in the first part we learned how to get a power series representation for a given function. For not every function but certain type of function related to this 1 over 1 minus x as sum of this power series, which is actually geometric series with common ratio x. From this, we can get 1 over 1 minus x squared as x squared to the nth. Instead of x, you have x squared. If you have a plus, then you can write it 1 minus x squared. So you can have stuff like this. Okay, we already done that. And a few more examples, which requires a little bit more manipulation, but in the end, it was all based on this. Okay? And then, toward the end of the first part, we showed that if f of x is a power series representation with a positive radius of convergence or infinite radius of convergence, then if f has power series representation, then f prime of x derivative also has a power series representation with the same radius of convergence, and that power series can be obtained by doing term by term differentiation. Okay? And indefinite integral or an antiderivative also has a power series representation with the same radius of convergence, and its power series representation can be obtained by doing term by term integration. So term by term differentiation and integration worked for polynomial function, but it works for power series too, just like an infinite degree polynomial. Okay? So we're going to use that theorem to get further. We are going to broaden the type of functions whose power series representation can be obtained, including from this. Okay? So first, example 4. What about this function? Now, it would be very hard to write it this way with simple 1 over 1 minus x. Okay, even if you force it like 1 minus, you can think of this. But that does not help. Look at this. You can force to say this one, but it does not give us any any understanding of power series, because when n is large, you don't understand. You don't know the form of this. This will create some of the lower order terms. So it's not the way you do this. In order to use this one directly, your 1 over 1 minus something, that something part has to be simple, so that the resulting series give us a clear understanding of the coefficient Cn of x minus a to the nth power. This one doesn't. So this is not an example you can use this approach directly. However, you should recognize that this is 3 minus x derivative. Okay? If you take the derivative, 3 minus x to the negative 1 power, derivative is, right, negative 1 times 3 minus x to the negative 2 times derivative of inside, negative 1. Negative and it cancel. So that's precisely this. And in the previous example, example 2, we learned that, so I'm going to write a derivative of, we already got this one as okay, with what? This one for absolute value less than 3. So this one had a radius of convergence 3. Okay. Then, according to the theorem we just learned at the end of the first part, because 1 over 3 minus x is this power series representation, its derivative function will have power series representation coming from term by term differentiation. The first term will be gone because constant term will be 0, so we can start from 1. Okay? So that means this is going to be 1 over 9 plus 2 over 27x and then 3 over 81. So 1 over 27x squared. Keep going. And radius of convergence is same as before. Okay? So we don't have to use this one directly. We use term by term differentiation of the power series representation of the antiderivative. Alright? This 1 over 3 minus x is an antiderivative 1 over 3 minus x squared. Okay? Now we can go further. Example 5. Find power series representation of the following function and their radii of convergences. A. ln of 3 minus 6. Again, when I wrote this note, my log means ln, not common log. Because in advanced mathematics, a lot of times we just use log to mean natural log, right? So I'm going to correct this. So this log means ln. ln of 3 minus x, and b, tangent inverse of x. All right. Now, a, ln of 3 minus x is actually the result of, if you integrate this one, 1 over 3 minus x, ln of 3 minus x, and derivative inside, this is just negative of antiderivative of 1 over 3 minus 6, whose power series was already obtained, right? So we can use term by term integration, right? By the way, we don't need to put absolute value of x because we're going to use what? Only this power series representation only for minus 0 to, remember, 0 to 3, minus 3, 2, okay? That power series was only working for this. So when x is here, this 3 minus x is positive, so we don't need absolute value sign there. Okay, then term by term so power series representation of an antiderivative obtained by doing term by term integration. We integrate this separately and add them up. Okay? That is some constant minus 1 over see? Antiderivative of x to the n is 1 over n plus 1 times x to the n plus 1. Alright? Okay. Now, n plus 1, n plus 1, n plus 1, everything's same. Starting from 0 means these number starts from 1. So if you want, you can write it as n starts from 1 to infinity over n times 3 to the n x to the n. Alright, you can write it that way. Now, we have to determine this constant. Well, by plugging x equals 0, what do you get? Left hand side, ln of 3. Right hand side, when x equals 0, everything 0. So c equals ln of 3. Therefore, ln of 3 minus x will be ln of 3 minus, or if you want, you can put minus over here. Okay? And same radius of convergence, obviously. Okay? So, we got the power series representation of this by recognizing it as a negative of antiderivative of 1 over 3 minus x. So its power series representation is just term by term integration of power series of this one. Term by term integration. So we did term by term integration. Alright? Okay. What about B? Tangent inverse of x. This is one of the antiderivative 1 for 1 plus x squared dx, isn't it? Right? Antiderivative. And in example 1, we found antiderivative of this. That was minus 1 to the nth, x would be 2n. Right? So by doing term by term integration, integrate this one term by term, minus 1 to the nth, 2n plus 1, x to be 2n plus 1. Okay? This is it. Now, how we get c? Again, because of x to be something, we're going to plug in x equals 0. Tangent inverse 0. But this one is also 0. So c equals 0. So tangent inverse of x is just, we got power series representation of tangent inverse of x, even though it doesn't look related to this at all, right? But through integration of 1 over 1 plus x squared, it was related. Okay? And radius of convergence does not change because this one had a radius of convergence 1. So it's indefinite also has the same radius of convergence. Okay, let me check the recording. Next, find the power series of, okay, let's do it over here. Find the power series of this x over 1 plus x to the 4th dx. And then B, use the result of A, approximate the definite integral of this, okay, to accurate to 3 decimal places. Okay, so in order to do this one, we have to find power series representation of this function first, and then we'll do term by term integration. Okay? So, first of all, x over 1 plus x to the 4th, just like before, we're going to use this one, x times 1 over 1 minus x to the 4th. Right? So 1 over minus something is, that's something to the nth power, and sigma. Okay? Like this. this one then can be written as minus 1 to the nth x to the 4n. So minus 1 to the nth x to the 4n plus 1. Okay? Alright, so if you want, you can write it as a few terms, n equals 0, so x minus x to the 5th plus x to the 9 minus x to the 13, and so forth. Okay? Now, then the derivative, antiderivative, indefinite integral of this one has power series which can be obtained by doing term by term integration. That is 4n plus 2 here, minus 1 to the n, x to the 4n plus 2. Oh, I forgot. Arbitrary constant c. Okay? So if you want to write a few terms, that will be c plus n equals 0, 1 half x to the square minus 1 over 6 x to the 6 plus 1 over 10 x to the 10th minus 1 over 14, keep going. Okay? So that's the power series representation of antiderivative. So you have arbitrary constant because this indefinite integral is a general antiderivative. So any constant would be fine. Now, if you have 0 to 1 half, that means, what is it? This one's from, right? This whole expression, plugging in x equals 1 half minus plugging x equals 0, right? We don't need constant because that will be cancelled anyway. Plugging in 0 will be 0, so this is just minus 1 to the nth over just 1 half to the 4n plus 2 over 4n plus 2. Okay? So you just replace x with 1 half, that's all. Alright? So let's write it. 1 half of 1 half square, 1 over 6, 1 half to the 6, 1/10, 1 half to the 10th, 1/14th. Keep going. So alternating series because of minus 1 to the nth. Now they ask us to find approximate value. This is, what is it? If you call it an, absolute value of an is decreasing. The larger the n, the smaller it gets, the absolute value of the sequence, and decreasing n going to 0. Two conditions for convergence of alternating series and alternating series estimation. We already knew that this is convergent because this one has x to the 4th absolute value less than 1, which is same as absolute value of x less than 1. Radius of convergence is 1, so this one also has a radius of convergence is 1. So x equals 1 half, obviously convergent. But important thing is alternate series estimation works because of those two conditions. Absolute value of an decreases and converges to 0. Therefore, wherever you cut, approximation due to that cut is the error by that approximation is smaller than the first term cut off. Okay? So here, if you look at it, if you cut it here, that will be your maximum possible size of error. And that size, okay, so this is, let's say this is S2, then R2 error size is less than or equal to 1/10, 1/2 of 10. This is 1024, so 1024 times 10, which is less than 0.0001, right? This is less than 10,000, right? Which is 0.0001. Okay. Now, what about S2 then? Our approximate value. So we want our approximate value to be correct within up to third digit. Knowing that your maximum possible error is less than 0.0001 is promising, right? What is S2 value? 1/2 squared minus 1/6, 1/2 to the 6th power is about 0.122398. Okay? Now, because the first term after the cutoff was positive, that means our true value will be a little bit larger than S2. So it's an underestimation. So your true value can be is a little bit larger than this, but no more than this much, right? Even if you add that maximum possible error, still it's gonna be 4958. So our true value will be smaller than this, somewhere between here and here. So whatever, that will be 0.1223 something or 0.1224 something. So if you do rounding with true value, still you're gonna get this. 0.223 or 4 will be just round off, right? Therefore, we can say the true value S will be, if you do rounding to the third decimal, it should be 0.122. Okay? Now what this is certain. We don't know exact value of S, but we know the exact rounded value to the third decimal because of this estimation of error. Okay? Now, final example. 7 is showing some function as a solution of differential equation. Okay? So let's say you have a differential equation. dy over x equals y. What does it mean? It's an equation satisfies some function whose derivative is equal to itself. The solution of this differential equation is a function, differential function, whose derivative is the same as y. So, y equals f of x is a solution to star, means that its derivative is itself, right? That's what you're going to do. Example 7. So in example 7, they ask you to show that this function represented by this power series. We know that this one, radius of convergence is infinity for this one because of n factorial. So we want to show that this is indeed a solution to this. Okay? So we want to show that this is a solution. That's why we have to show this. So let's show this. F prime of x, derivative of what? Now, when your function has power series representation with this radius convergence, then the derivative of that will have term by term differentiation, right? I'm going to rewrite it here. So that would be 1x squared over 2 factorial, x to the third of 3 factorial, x to the fourth of 4 factorial. Keep going, right? If you do term by term differentiation, that will be starting from 1, this constant term will be 0, n times x to the n minus 1 over n factorial. Okay, which means, n over n factorial, what is it? N minus 1 times n cancel. N minus 1 factorial is remaining, right? Okay, starting from n equals 1. That is, if I change n starting from 0, see, actually something over same thing factorial, starting from 0, isn't it? Right? I can rewrite it this way. Same as the starting one. And you can see this over here. If you do this, derivative of 1 is 0, derivative of x equals 1, derivative of this one is x, 3 cancel, x squared over 2 factorial, 4 cancel, x to the third of 3 factorial, 5x to the fourth, 5 cancel. Indeed, you're going to have the same thing as we saw here. That is exactly f of x. That means whatever this is a solution for this. Now, later in section 8.7, we will show that this is a power series representation of e to the x, actually. All right? We'll show that in the next 3 video lectures. We're going to split, I think we're going to split section 8.7 into 3 parts. Maybe it could be 4 parts, 3 or 4 parts. So we're going to see this one later. So anyway, so this function represented by this power series turned out to be a solution of this differential equation. Okay? Alright, that's the end of video lecture, second part of section 8.6. So that's the end of section 8.6. So next time we will start covering 8.7. Alright? Okay, see you next time.